Right, so you'll notice that up until this point in the curve sketching notes, what we've pretty much had is functions that have been continuous with no domain restrictions or discontinuities. We saw a few of them that did have some cusp in there that we had to be concerned about where it was not differentiable, but they've been continuous kind of throughout. So I thought we would throw in an example here where you're looking at it and go, wait a minute, we have some discontinuities on this graph. So the minute that we see that we have this nice rational function, you go, okay, I have some discontinuities. So remember that once you know you have discontinuities, our domain is going to be x such that x does not equal plus or minus 2. Or no, if you want to do it with interval notation, negative infinity to negative 2, negative 2 to 2, and then 2 to infinity is going to be your domain. So this is f is continuous on its domain, which is highlighted above, because you have a rational function. And so the idea here is that you also need to classify those discontinuities. So this is a review of when you have removable or non-removable discontinuities, you're going to have to determine that. And remember, you do that by factoring our original function and seeing if we can remove the factors that belong to those discontinuities. So x cubed plus 8. And if you forget when you're looking at it that you can go ahead and do long division on factoring this, but you do want to kind of pay attention to the fact that it's a perfect cube difference or sum or difference of perfect cubes. So it is one of the factorings that you should have memorized. X cubed plus 8 factors to x plus 2, and then x squared minus 2x plus 4. And I'll leave that for you to check. If you did not remember that is how it factors, what you would have done is you could have plugged in, you know that negative 2 plugged in is 0, which is why x plus 2 is a factor. And then you could have done your synthetic division with 1, 0, 0, 8 and run through, drop your 1, 1 times 2 is 2, subtract, negative 2, multiply 4, subtract, um, oops, negative 4, subtract, which is going to be 4, and then multiply. I'm sorry, I'm supposed to be adding. It'd be nice if I remembered my own synthetic division before I started this. So um, drop the 1. X plus 2 means the 0 is negative 2. Sorry, that's what it is. So negative 2 add, negative 2 multiply, add 4, multiply negative 8, and gives you 0. Okay, so there's a quick review. We've both remembered what synthetic division is. So you get that, and you see that this one is removable. And when you're removable, we know that there is a point discontinuity, which is going to give us a hole at negative 2, and we'll talk about how to find the value for that. And we know that there is a vertical asymptote, infinite discontinuity at x equal to 2. So that's kind of how you figure that out. To get the value of where this is Fred reduced function. And so I could plug in negative 2 into here and get the value of the hole and where it's located. All right, and then if you check your math on that, plugging in negative 2 is going to give you negative 3 on that. And then if you remember anything about your difference and sum of perfect cubes, this also, if you check your discriminant, it does not factor, does not have any real zeros, so there are no x-intercepts on this graph, okay? Now, the other thing, which is also still pre-calculus, is the end behavior of the graph. So we would like to do the limit as x goes to infinity of f of x. And we can do that survival of the fittest, and you can actually do both plus or minus because um, it's a rational function. So when we do this, it's going to be the dominant term over the dominant term, x cubed over x squared, which is going to be x, which basically tells me that we can do the left and the right side by following the line x. That's going to tell me that there's also a slant asymptote. And it's a slant asymptote because you have a linear term when you simplify that. The degree on the top is exactly one more than the degree on the bottom. That's how you know you have a slant asymptote. So we know that the limit as x goes to negative infinity of x is going to be negative infinity, but the limit as x goes to infinity of x is going to be positive infinity. Now, we've got the end behavior, but since it has a slant asymptote, we would like to be able to sketch it on the graph so that we know exactly where it is. And to get the slant asymptote, that's where you use long division. You're going to take your x squared minus 4 and you're going to divide that into x cubed. I like to do plus 0x squared plus 0x plus 8 and go ahead and do the division and get the slant asymptote. So x times x squared is going to give me x cubed minus 4x. See that way, so you can line it up. Remember, you are going to subtract. And so when we subtract, that goes away. This is going to be 0 minus negative 4. That's going to be positive 4x plus 8. And then I go, well, how many times, what should I do? Do I do plus something there? But see how this degree is larger than that degree? This is actually your remainder because it's a smaller degree than your divisor. So we know, like following this, that x cubed plus 8 divided by x squared minus 4 is going to be x plus your remainder, 4x plus 8 over your divisor, x squared plus 4. And when you do the limit as x goes to plus or minus infinity, this is always going to go to 0. And so whatever is your quotient is going to be your slant asymptote. So whatever ends up in this spot is your slant asymptote. And not always, don't always think it's going to be just x. It could have been x plus some constant right here, but the answer was we ended up with a constant of plus 0 because the degree here was smaller. If that had been 4x squared, it would have been x plus 4 would have been the slant asymptote. But for this one, it just happened to be y equal to x. So y equals x is going to be our slant asymptote. And so all of that was pre-calculus. Haven't even started the calculus yet. So now we're ready to start the calculus. Now to help myself out in the calculus, you definitely want to use Fred, the reduced function, because that will make it a little easier for us as we go to find our derivatives, because the only difference between the original and the reduced one is the whole. So we've already noted that we have a whole, so we can use the reduced one from now on. So our derivative is going to, using quotient rule, low b high 2x minus 2 minus high x squared minus 2x plus 4 d low, which is 1, all over the bottom squared, x minus 2 squared. I'm just going to go ahead and multiply this out. It doesn't have any factors because remember that doesn't factor. So let's multiply and collect like terms. So this would be 2x squared minus x squared, which is going to give me x squared. And then we're going to have minus 4x minus 2x, that's minus 6x plus 2x, which is minus 4x. And then we're going to have our plus 4 and our minus 4, and they go away. So that's kind of nice. X minus 2 squared. So our critical values, the derivative is equal to 0 at if this factors, right, you can just rewrite this as x minus 4, x minus 2 squared. So x equal to 0, x equal to 4. We do know that it does not exist at x equals plus or minus, or at 2. Well, remember plus or minus 2, because I got a 2 from here, and remember we have the whole at negative 2. These are not critical values. These are not going to be extrema because we already know that we have a whole and we have a vertical asymptote. You can still switch signs on your derivative at these values, but you want to make sure that you include them in your sign chart, but you do not want to make sure you pick them as extrema. So we have -2, 0, 2, and 4. And so remember, this is our vertical asymptote. This is our hole on, maybe I should write those below and not above, because that's what's happening on F. They were undefined and undefined. So that one was your hole. That one was your vertical asymptote. So I want to make sure that I do that. And then you had your 0 here and here. So we go ahead and we do our signs going across. If I pick something like -10, that's going to be positive on the top. And on the bottom, it's going to be positive. Well, the bottom's always positive because you're squaring it. So you really only have to look up here. And so it would be plus, minus, plus in the quadratic around the 0 and the 4. So it would be plus, minus, and then plus after the 4 because of the parabola part that's there. So in taking a look at this, we know that we're going to be increasing, hit the hole, keep increasing, and then you're going to be decreasing. So we have a relative max at x equal to 0 because f prime switched, plus 2 minus, and then we're going to be decreasing after the vertical asymptote, and then we're going to be increasing, so there's a relative min at x equal to 4 because f prime switched minus 2 plus, minus 2 plus. Okay, so now our second derivative, we're going to do low d high, 2x minus 4 minus our high, x squared minus 4x d low, which is going to be 2 times x minus 2 to the first times 1 all over the bottom squared, x minus 2 to the fourth. Now I'm going to, in the interest of time, I'm going to simplify this off the screen, turn it back on, and let you check your answer. So you guys pause, simplify, and then come back. And as complicated as that was, when you pulled out, I had a 2x minus 4 and a 2x minus 4 here, and then simplified the inside, FOILed this out, collected like terms, things canceled out, and you ended up with 8 over x minus 2 cubed. What I know from that is that there are no points of inflection before I check anything because there's no place where you're going to switch sign that was not already a discontinuity. Because remember, your x equal to 2 and your x equal to -2 are your discontinuities, and that's places where you can switch, but they are not going to be places where you have a point of inflection because it was a discontinuity on the original. Now remember, the 2 is coming in here, and the one thing that I remember I took out, you've got to remember that there's technically that exception on all of these because I took it out up here, that it's this where x does not equal -2 because of the hole. And that continues when you get to this derivative and you find this, it's really where x does not equal -2 in addition to the 2 that's shown there. That exception follows it all the way down, okay? So you do want to go ahead and do your sign chart with your -2 and your 2 because you want to see about your concavity changing. I'm going to pause because I'm running out of time. Magic, here's your sign chart. Remember, you have the -2 and 2, your hole, your vertical asymptote, down, down, concave up. All right, so using Desmos, here's our slant asymptote, here's our vertical asymptote, here's the hole, here is your relative max, and there's your relative min. And you kind of pretty much know it's going to be following this and following these guidelines here. So it should be no surprise when we turn this on that here's the shape of our graph for this example. And we can basically connect the dots that we have. All right, so that will end up example 9, and we have a couple more examples in these notes.